I'm so nice now. I could be way better if it's now one.
Okay, and welcome to lab 11. In this lab, we'll go over how to solve part of the simple PDEs in Python and Fourier series, because PDE is very hard to solve, and some of the harder PDEs is currently research topics. So we're only going to tackle some of the simpler ones. So before we dive into the Python, we want to first review the concepts. So for partial differential equations, you're taking derivative not only with respect to one variable, but with multiple variables. For example, you can take with respect to positions x, y, and z, and you can also take derivative with respect to time. In this case, let's look at the 1D wave equation, where we have u taking derivative twice with respect to time is equal to c squared times u taking the derivative with respect to x twice. And because it has a second derivative with respect to position, it has two boundary conditions. Because it has second derivative with respect to time, it also has two initial conditions. And we'll make the boundary conditions 0 and make the initial condition f of x and g of x. So this is the governing equation. Second order derivative with respect to t is equal to constant square times second derivative with respect to position. We have our boundary condition and initial condition. To solve it, we first separate the variables, assuming that they can be multiplied with each other and separable. And then after some lecture derivation, we arrive at two ordinary differential equations. And after imposing the boundary condition, we get the eigenfunction where this is two constants, and then the constant multiplied by cosine and sine. And so this is our final solution. So this is quite intimidating without visualization. So this next guided problem is to look at how we visualize this in Desmos. So after this lab, when you encounter something very complicated like this, you are able to visualize this with Desmos. So the first question is, when t is equal to 0, change the n. And so describe what the solution changes in terms of its shape. So currently the time is 0, and this red curve is the solution curve. So n is currently equal to 1. As I increase the n, let's see what happens. So when n is 1 and n is 2, it's the same. But as I increase to 3, there's more oscillation. So that's from the cosine sign. And as I increase the n, you see that it's getting more oscillation, but the amplitude of the oscillation decreases. And it's approaching to some value of 1. And this is because we're setting the initial condition f of x is equal to 1. So it's supposed to be like all 1 instead of this oscillation. So this is expected. And compare the solution from n is equal to 1 to 3, 4, 5, 6. So we saw that when n is equal to 1 and n is equal to 2, they're the same. And the reason is because of the constant here. So when we do the math for the constant, when b and b1 and b2, they will be result in the same curve. And same with 3, 4, and 5, 6. You can change this to 3, 4, they're the same. And 5, 6 are all the same too. That's the result of the constant. And now let's set n is equal to 3 and change t. So if you change t, this is with respect to time. So what it does is that it oscillates over time. So over time, the solution goes from positive to near 0, and then to negative, and then oscillates back up again. And then freely explore different n and t, does the solution curve match your expectation of the initial values? And recall that initial value, the fx, is defined as the initial value of the original equation, and g of x is the first derivative. And we define fx as 1, meaning that initially everything should be equal to 1. So it should be a flat curve that's y is equal to 1. But what we observe here is not y is equal to 1. Instead, we observe an oscillation. But as n increases, it approaches this 1. So if we do, so currently at 15, it's having a hard time to calculate because it has a lot of calculations. But as n increases, it approaches this constant 1, but not exactly. Only when n is equal to infinity, it will be exactly like 1. But when n is finite, it's just an approximation to this initial condition. Okay, and these are the solutions that I've written out. And you can also try with some complicated initial condition. Instead of a constant 1, you can try this exponential term, and you'll see that Desmos slows down very fast. So for example, here we have n is equal to 15. It's already having a hard time to calculate the solution. And that's why Desmos is only for getting the intuition for the solution. But what we really need is Python to look at the details of the solution. So in the next problem, we will plot the Fourier series solution of the same system used in Desmos, but instead now we're plotting this in Python. So the constants are defined, initial conditions are defined, and we define some points for x and points for t. And we want to plot the solution. So the hard part is how to convert this mathematical expression into a function. Okay, so let's do that. So let's first define the constant c is equal to 1 and L is equal to 1. F of x, even though it's a function, it is a constant, I still define it as a lambda function with respect to x, and it's equal to 1. And the same for g. So g is a lambda function with respect to x, and it's a constant 1. And then I want to define the x. So x minimum is 0, and x maximum is L. And we already defined L as 1. And it has 1,000 points, so x length is 1,000. So I have x is equal to NP Lin space 0, so x minimum to x maximum with 1,000 points. I can do the same thing with t, but instead this time I have from 0 to 1 with 100 points and change all the x to t. So now I have defined a list of points for x and a list of points for t. And then the number of eigenfunction superposition. So the sum, we're not going to sum to infinity, and instead we're going to sum up to some finite number n. And in this case, n is equal to 100. So we will sum up 100 of these terms. So after defining the constants, we can write out the function. So this is a much more complicated function than just sine or cosine alone. So what we need instead is to define it as a real big function. So def u. So this is how we define a big function, and it will return something. And inside of u, what do we need to take in? We need to take in the n as a parameter, the x, and t. And then we want to first get this term done, and then we'll sum up all the terms. And within this term, we have different constants. So let's first code up the constants. So here's an integral. So we'll code up the numerical integral inside Python. So let's first focus on the integrand. So what's being integrated? So I'll say b integrand is equal to, I'll define it as a function. a lambda function, and it will be f of x times np sine times n pi times x divided by L. So this is the integrand that's being integrated. And this takes in the argument of x and n. So it depends on x and n. And L is a constant we already defined as 1. Now do the same thing with b star. So b star integrand is a lambda function, and it's g of x times sine of n pi x divided by L. So now I have coded up the integrand. Now we want to do the integral. So how do we do the integral? So we haven't really officially taught numerical integration, but we can always search up numerical integration in Python. So to do integration in Python, you can use the scipy.integrate package. And inside the package, the first method is for general purpose integration. So you can use the command quad. So what you'll do is to search that command. So this gives some examples of how to use it. So basically, you need to supply the function or the integrand that you need, which we just coded up, and you'll give it 2 bounds. So because this is a definite integral, the bounds are from 0 to L. So a and b will be 0 and L. And this args means that if there's additional arguments, you'll put the arguments here. And here we have an additional argument of n. So to integrate this, let's give it an example. So integrate, so quad, give it the function, and the function is the b integrand. Integrating from 0, so x minimum, to L, which is x maximum, and then give it an argument because we're not only integrating with respect to x, but we're also changing the n. So let's set n equals to 1. So this gives out a tuple. And the first value is the solution. The second value is the numerical tolerance. So we only want the first value, so we index 0. And this will be the result of integration. Okay, so we have accomplished this part, the integral part. So I'll just multiply by 2 divided by L, and that will be b, the constant b. I'll do the same thing with the constant b star. B star is 2 divided by c times n times c times n times pi times the integral. So that will be the command quad. I'll supply the function, which is the b star integral, b star integrand, integrating from 0 to L, which is x minimum to x maximum, and then give the n, say 1. And then I'll extract the first value. Okay, and these b constants, I'll also make it a lambda function. And these will be a function of also, oh, here I didn't put x and n. And these constants will also be a function of, it's not a function of x, but it's a function of n. Here, substitute with n. And so if I do so now if I call the constant b, I have some n. So let's let n is equal to 1, I'll get some value. So that will be the constant b of 1 is equal to this. And b of 2 will be equal to this number. B of 3 and B of 4. And you see that there is a pattern that shows up. So if you have B of 1, 2, 3, 4, you see that the second and the fourth one, so the even constants are 0. And you can also try the same thing with B star. So even constants are 0. And this again explains why n equals to 1 and n equals to 2 are the same, because when n equals to 2, the constant is 0. So that reduces down n is equal to 1. Okay, so now we defined the b constants. Now we want to define this whole term. So I'll define this term as u of n and define it as a lambda function. That's with respect to n, x, and t. So that's b of n. So b of n times cosine times inside that has lambda of n. So lambda is a function, but lambda is also a keyword. So what I do is to add a underscore to make it a variable with respect to n times t plus b star of n times sine of lambda underscore of n times t. And everything multiplied by sine of n pi x divided by L. And here I have to define the constant lambda as a lambda function. And this constant lambda we defined as c n pi divided by L. C times n times L, c n pi divided by L times pi divided by L. So this only depends on n. If we run it, we can try some numbers. So say, try a number. This should also give me a number. Okay. In the next step, after we have u of n, we want to sum everything up. And to do that, I'll say a sum terms. I'll initialize it with zeros like. I'll make it. So I'll have u of n, say n is equal to 1. I'll supply the x and t. Cannot broadcast together. What is x and t? So x has 1,000 points and t have 100 points. And it's causing the problem at u of n. So at this step, there's something that's wrong. Cannot broadcast together. So when we have this type of error, what we want to do is to break the problem down. So see which part has problem. So this part, say I have this has no problem. Now we'll see if this part has problem. Okay, this part also has no problem. I'll try this part. I'm changing the n to some number. Okay, so this part has some problem. So this part is okay. This part is also okay. So this shape is 100, and this shape is 1,000. So these two cannot be broadcasted together. Interesting. Cosine of t. Okay, so what's going on is that I have different numbers of x and n, but I only define it as a list. But instead, I'll need to do the same thing when we have the face portrait. I'll need to make a mesh grid of x and n's so that their dimension matches. So currently I have 1,000. So the shape for x is 1,000 and the shape for t is 100. They cannot be calculated together. What I need to do is to use NP mesh grid and make x and t the arguments. And now I will get an array with the same dimension. So there will be big X and big T. and the big X and big T will have the same shape of 100 times 1,000. Not really, because this is intentional to make it not the same, because in reality, you won't always have the same numbers. So to solve the problem, you need to use mesh grid. And instead of putting in just lowercase x and t, you need to put in uppercase x and t so that they have the same shape. And so now it solves the problem. So the mesh grid command is also needed. So now u of n is fine. So I'll do a zeros-like command with u of n. So that will create an array that have the same shape as this, but it's all 0 to initialize the sum terms. And then we're summing from n is equal to 1 to n is equal to 100. So I'll write a for loop for I in range of n. Let's first print n. Oh, I haven't defined n, so it should be big N. Let's print I. So it starts at 0 and ends at 99, but we want to start at 1 and end at 100. So what I'll do is to change the range. So range from beginning at 1 and ending but not including n plus 1. So now I'm starting at 1 and then ending at 100. So what I'll do is to update the sum terms to what's already being summed plus the new term u of n with respect to n is equal to I, x, and t. And after some calculation, you get the summed terms. And this will be the final result. And of course, we want to package this all into a function. So what we'll do is to define this u function and put this all inside. So this defines the constants. And this defines the eigenfunction of a single n. And this is by the principle of superposition of different eigenfunctions. And when we define these functions, we have to return the things that we want as a result. And the result is the summed terms. And to test this, we can try u of, say, I'll sum up to 200. Let's say just 20. And then big X, big T. And it should give me some result like this. And the shape should be 100 by 1,000. Okay, that's a complicated example, but any question? Yes, so the zeros-like is similar to np.zeros, but for np.zeros, you input the dimension, so 10 by 10, so or 2 by 10, like this. But np-zeros takes in an array. So I'll say what? X of 2 to 10. So this is an array with a shape of 2 by 10. So np-zeros, you take in that array, it will generate an array with all zeros, but with the same shape of the array that you inputted. So basically, it extracts the dimension of this and then inputs to np-zeros. So it first does is to get its shape, which is 2 by 10, and it inputs to np-zeros, which gives you the same value. Oh, this should be zeros. Zeros-like takes in an arbitrary array, and it gets the shape. So zeros-like is equivalent to, if you have, so this is our array, right? So it first gets the shape. and the shape is 2 by 10. And then it inputs to MP zeros with the shape. So these are equivalent. It says just a faster way, so you don't have to extract the shape. Okay, so now we have written the function. So this is quite complicated in Python because we need some numerical integration and we want to sum this up. And to sum it up, we use the for loop. And for the constants, we use numerical integration. Okay. So we have the constant, the function, and now we want is to find the solution. So plot the solution u of xt in a 2D heat map. So I would say the approximate solution, because we're only approximating it to some n, we can't do infinity. In this case, we'll do n is equal to 100. So what we'll do is to get an approximate solution of u, and the n is equal to 100, x and t. And you can verify the shape of approximate solution should be 100 times 1,000. And then now it's plotting. You don't have to know all the plotting commands. That's why I have the examples, so you can copy and paste. But basically, I will do is to first generate an axis, subplots. And inside the axis, 5, 6. Inside that axis, I will do IM plot. IM stands for image. An image is basically an array. So what it does is to, IM show. So it will show the image of the approximate solutions. And this is the solution, but it looks weird. So we'll need to get some additional commands. So say the aspect, make it auto aspect. So now this is the solution. And then the extent is equal to x minimum to x maximum, t minimum to t maximum. And then, okay, so that the center is at the lower left. And then the colors represents the values. And currently we don't have a color bar, so let's add a color bar to the figure. There's no attribute, color bar. Mappable. Okay, I'll define this as IM, so image, and input the image. So you can copy and paste this code from the example. But what it does is that it uses this color to represent the height of the function. And then of course we want to label this. The X label should be, so here is from 0 to 1. And it has 100 points. And that 100 points, I think, is the X. Oh, it's the T. So the X label is T, and the Y label is X. So let's make it more intuitive and take the transpose of it. Let's see. I didn't take the transpose, okay. So I'll label the X label as X, and the Y label as T. Y label as T. Oh, I think I need an additional command to set the origin. So the origin should be at the lower point. Okay, so what this graph is telling us is on the x-axis, I have the position x. Remember, this is an 1D wave equation problem. I have a 1D string, and I plot the string, and how does it move over time? So on the y-axis, I have their evolution with respect to time. So if we cut horizontally, this is a time slice. So at a particular time, what does the string look like? If I cut vertically, if I cut the position slice, that will be at one particular position. How does it move over time? And this tells us that the amplitude is the highest in this region and the lowest in this region. So the amplitude is highest when time is in the beginning and lowest when it's at the end. So the 2D heat map might be a little bit abstract. So let's also plot the time slice and the position slice. So this is the problem. I'll just copy it. So plot the time slice in a line graph where the time indices are these. So time indices is MP. Let's say this is a range from 0 to 100 with a spacing of 10. And you can check by printing it out. It should be like this. And then in the figure, I'll plot something. And I will plot with a for loop for I, T of I in time indices. I'll enumerate this. And you can see if I print I and T of I. So I is the current iteration counter, and T of I is the time index. And what I want to plot is, because I want to take a time slice, I want to look at the approximate solution. Okay, what did I define? Approx solution. No, I misspelled. Approx. So I want to index this at different time indices. So I want to index it at different T of I and then output everything on the position. And I'll plot this here with respect to X. So X dot plot. And these are the solution. So this on the X-axis is X. And on the Y-axis is U. And we also want to label this so that we know which one is which. So label this with the T of I. T is equal to T at the T of I. Okay. And these are all the floating points. So we don't care about the floating point, so we can round it. So we'll round to the nearest 10. And I'll place it outside. And these are a little difficult to see. But what it does is that when T is equal to 0, it's the initial condition 1. And when T evolves, it goes up like this. And then when T is equal to 5, it becomes this triangle curve. And then it oscillates up, and then as time goes, it oscillates down. And then if you do more time slices, it will be oscillating up and down, up and down. And I think we can also define a color map. So this is more advanced, so you don't need to know how to do it, but you can copy this and to look at and use the color labels. So it's more easy to understand. T colors of I. So basically you can look at the color and see which one is at lesser time and which one is at higher times.
Not the boundary is fixed at x is equal to 0. But since at x is equal to 0, there's no points.
when x is equal to 0.
Boundary. Zero. You have zero.
Yes, these are the boundary conditions.
Not showing that.
So the Fourier series solution satisfies the boundary condition. So this is at when the x, oh, sorry, the label is wrong. This is label y. So when x is equal to 0, it is at 0. And when x is equal to L, which is 1, it's also at 0. Yeah. And for all the solutions, it all satisfies this initial condition, the boundary condition.
Why is it? I mean, the triangle shape thing.
The triangle shape. I think the triangle shape results in the specific combination of cosine and sine terms. So when you have specific combination of those, you can create these like rectangular waves or these triangle waves. It's just that the constants has to be specific. Good questions. And here are the time slices, but we can also do position slices. So these time slices are cutting horizontally when we look at particular times. So I'm slicing at here, 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 here. But what if we cut vertically? So that will be the position slice. If I cut the position slice here, I can copy and paste this. I'll just need to change the parameters. So here will be the x. And for the x, I want indices from 0 to 1,000 at the time step of 100. And I'll enumerate the x. But here, the solution, I'll index at the x position. This should give me the result. Okay, x and y must have the same dimension. Okay, this should be plotting at t, different t. So this is at different t. So I cut vertically at different x. So what I have is at one position, how does it evolve over time? So we see when x is equal to, okay, here's wrong, it should be x of I. So when x is equal to 0, which is the boundary condition, it's 0, which satisfies the boundary condition over time. When s is equal to 1, 2, 3, I think it's being obscured. So it's under this curve. But as x increases, you see that the amplitude is different. But the shape is conserved. So increase, back down to 0, constant, and then negative. And you can see at different position slides how it evolves over time. The frequency? You mean if I change the numbers? T to 100. Great question. Yes, I think so. So I think it will oscillate. So this, I think, is one full cycle. So that will be requiring it to, say, integrate to 2. So it's convenient because we can run this over and over. Huh. It's not. So interesting. Okay, we'll figure out this later, but Currently it's time equals to 1. Okay. And so we have looked at the position slice and the time slice, and we can also plot it in 3D. And you are not responsible for the syntax, but you can copy and paste the code to see the 3D slice. So this shows that when t is equal to 0, it's positive value. And as t evolves, more and more values are concentrated at the top and in the middle, and the others are 0. And then when t passes through half time, it goes to negative values. Okay, any questions? You can try this with the practice problem where we have another equation, so the heat equation, and we're given some analytic solution, and this problem is letting you to visualize this in Desmos and visualize this in Python. And you can copy and paste the code for visualization, but the solution for the analytic solution you need to code up by yourself. So you want to index this. Like this is X.
I just used index code, like for the operation, and then the different one. So I added one C.
The number of points, I think it's assuming, okay, so it's not written on the problem. So if these are assuming that the time you have 100 points, and for position you have 1,000 points. So the X will be 1,000 points. It's not a problem. I didn't expect that. Because it's science.
Yeah, there's no errors.
Hopefully that should fit in the contract because I didn't specify.
So we want time the day before,
That's crazy.
or the day before,
That's
or no,
that's
Tuesday.
That's
It's so easy.
The boundary condition is under the doesn't equal to 0. Seriously.
Oh, but I just used this.
Oh. These are you bet. So that's the first thing that means. But you're setting these are original. If these are the original function.
So how do I express the first language?
No, that's a mystery.
Me too. I got
So you-
I'm literally it's like number 3 out of like 24. We got the worst time, that's
So-
why. I'm also waiting for math, no, I'm not worried.
Two.
It's like, I'm one, waitlist
So
number one
this
out of
has-
7 things. Oh, so I'm like,
I know where
so physics, I'm like, I know this Victoria. You know, it feels rough, but I'm like, yeah, yeah, hopefully. No, I just don't want to be like, do you remember, like, you take 7 eggs, for instance? Like, you know, I would pay anyone to get to 7 eggs. But I mean, I won't do that, I'll just take it, whatever. Yeah.
You can only go forward, so I can take the price plus that.
Yeah,
Twice.
like 2 times. Yeah,
Two plus that times two plus that. divided by-
I also kind of forgot about our shift.
So that will be, because
I
we're
like-
actually left on.
I was so good at
That's
that.
index to zero.
No, I like it.
I had like a
Two
deadline,
times
they sound like
U of T index to zero. Minus
Oh, that's a good idea.
U of
No, I
T.
literally-
Yeah.
I had an alarm that went off,
This
but I was
is
like,
plus one
I
minus
was like,
zero.
I didn't set an alarm for today. What if I want to play Snitch? And then I woke up at like 10 because my thing was at 10 and then I woke up at 10
U
like
of T.
so I was scrolling through the shit and one of my friends posted like, oh my class, and I was like, oh, it's funny, that's tomorrow, right? And I was like, wait. Yeah, but it's okay, it didn't make much of a difference, there's nothing left.
So you
I mean, no one wanted me to be class, obviously.
You are
Good job.
Or phase tuning,
this is next.
yeah, phase
You are
tuning,
one.
158. I'm assuming, no,
But two times you.
we'll see. I mean, if physics can't happen, I mean, it's not my fault.
You have your one minus two
It's just,
times. You are
I don't know.
the whole thing about 50.
Yeah.
By the whole-
I think he's taking 54 right now, and taking 54 this year, so I think they said it should be okay.
You are okay.
If it's -1, and then the quiz is on. So at least last year, my kids were all
Right
like,
now,
yeah.
you can't go forward.
Yeah, I also have lab that day. So.
This times X minus that.
That
That will be
was really,
L, that will be minus.
but if I get everything I
So
want. I
it's
would-
minus three. Minus two.
So I don't know why 9 a.m. just feels so much better. Feels more-
Minus three. The right.
I think it's like an hour and a half,
Yeah. Even like, I think hour and a half classes they can. I'd rather have it, I think I'd rather have it. But like the physics class, 70 or whatever, it's like, that, it's all the lectures like that. Like 2 to 3:30. But this is on that Stewart something. I was just like, I took math during that time and it's like the group shit. Yeah. Yeah. That's why I had my math class last, or freshman year. Yeah, it's right after lunch. Where it's like. But at least it's not, what were freshman year, first semester to take, right, to take category nothing. And I was from 6, I hated that, yeah, or those from 5 to 6 or 6.
I don't know, but it was like dark.
Yeah, it was dark when we get out, and I was so small and warm.
I was scared the first time I went there because it was like,
Yeah,
Oh,
I
like,
was like, this building's gonna work. It's not.
You must see the columns and to be.
I just can't forget. It was so cool. I know.
I
It's
guess
so
I
weird.
was like actually.
But I was like, wait, why can't computer just make it work?
It's not intuitive.
Oh my god, especially compared to any other. Like this is hard. like maybe try to do something.
So like also an A is when you do like a force diagram.
Yeah.
So it's like.
It took for a while for me
This
to.
is kind of like easier to wash it, and it's like, it's
Oh,
or at least I know 70 is like. And like if you don't know how to do
So
something,
just leave it.
yeah, I was just like, right, thank you. I'm gonna give you something.
Okay, so we got it. The question is with the follow because I think it's something to do with how you thought of this. Whenever I actually get my graphs, it's like all blank.
So. You look at the slices. So this is like 1 into so it's basically 0. So this is the box.
This is, oh yeah, sorry.
So when we. Or. One for the personal, it's like kind of easy.
I did experiment with that. It gives the same thing, just a different color. Maybe like this one's good. This one's good.
Interesting. Let's do it. So 4 divided by 3 times first. That's minus n squared, so there should be. Minus n squared. N squared. So what is the G? Oh, yeah. So that's good. Oh, that's it. Team. Team variable.
Did I just write it down?
But you have everything behind the solution. One by 1.3 inside the sum, which is fine. Oh, and so the first part we define as n. That will be whatever n it is.
Right.
But when we're doing iteration, we're changing the n, so that should be I. So you should define this n, the first part, as a lambda function with respect to n. Because it's taking this n directly to here. So if you input 100, this first part will be a constant throughout. So instead, we should make this a lambda function with respect to n. We have also always with respect to so n equal to 1, then be 100.
Could you go on this? Can you go ahead and stop?
Retreat.
I don't know, change the concentrate. It's vegan.
This
It's easy. It's gonna do this thing that it's like choose just cancel this. It needs to like run the sound but I only it's like
for the
It's not oscillating. It's oscillating.
urgent. Since vegans.
PDE is hard to solve, it's really hard to use. That's why.
You also know why we're taking the.
Saturday. Next week is this week, isn't it?
So
Sunday.
for PDE class. I think we're avoiding something about making it solve separately. Because for the separate, you move this to the left, and then this becomes positive. Positive. So that's why we treat these
All day.
changes. It's not positive. It's this. It doesn't matter. If
Yeah.
Plus sign.
Friday night. Usually.
That's the
Okay.
So like, I don't know.
But if we
If we finish it, we can do that. Yeah.
That's the contract.
Yeah, anything else? Yeah. See, I already.
I didn't see it.
Well, you don't have to send it.
Okay.
So we can go to the meeting.
I'm going to use this.
Here it says he dated girlfriend.
No, the 20.
But then also the thing. Did you see that this week?
Yeah,
Okay,
shade
go
on.
home. Is it again this I should do? I guess it's kind of far for her too.
Yeah.
Like all the way down.
Give us to some.
I passed by San Jose and then better exam.
You see it?
No, I was on the one where there's 17.
Studies, you said this.
Oh my God. I almost fell asleep yesterday.
Oh, no. You're trying by yourself.
But you said.
My friends are saying all of it.
They're so bad.
Jack's attorney. There's actually something in PR. I haven't been there in like 3 years. So.
Just go to the boardwalk or just.
And I went to downtown. And I went to campus. With my friend. She lives in like one of the concept. Both her roommates are like CS majors, but one was CS gaming. They have a CS gaming. They gave us they use it.
Wait, Southwest has this thing where. It's like a film, you can find it.
Yeah.
I know they have like a lot of raves in the board.
Oh, really?
But they don't have sororities and stuff. Yeah, they have raves and.
So.
And where are you supposed to go? And then.
This should be.
This is like the opposite.
I don't know if they're necessarily important. I'd say like compared to like Santa Barbara.
I think it's tough one.
Maybe that. I mean, they don't have much to do other than rave in the forest or like do school. Cause like there's, if you don't have a car, that's really, yeah. Cause like the buses are overwhelming and you can't walk, but, or you could walk, but you might get hit by a car. Because there's no sidewalk, so to get out, so, I get out like this, so you can get to downtown.
Let me go back to the.
So, yeah.
Isn't.
But it's nice, I mean, it's like summer camp. It kind of looks like, I used to play with concerts, it's really fancy, it's like we just go there, but it's like, but it was like,
That
Sure. But like, it was kind of like, it's like in the board, it was like a boarding school. No, we put on their field. And then they would feed us, so it was Wang and Stella. So she was really good. And you don't know her name, because when we'd be playing, they'd be screaming. "You get the ball, Stella."
Okay.
Oh, it's a little. Oh, yeah, this is their field. Oh, yeah. It's like Spanish. The thing is, for how nice of a school is.
Yeah, I thought.
Like it's real grass, but because it's California, there's no water. Ta-da. It's super dry. It's your high school.
Yeah, that makes sense. Usually.
See, so we have a pool. And like the middle, we have a pool in the middle.
So
we
rich.
swim, everyone can walk around. It's not. That's what this one keeps it.
Or
You have a really small school. Two.
let's do.
Oh, yeah. You know, all, these two.
Wait, actually, I'm seeing.
Should be. We have the file. The size one.
Oh my gosh, you know my cousin is dating the athletic director's son. My cousin is dating the athletic director's son of my school. She's practically like my high school girl. If they get married. I think that'll be really.
Yeah, I can try to work it out in the other one, thank you.
Do you guys have lockers?
Nope.
Okay, any problems when solving this? So the main thing, so everything you can copy from above, the X and T, the plotting, and the only thing that's needing to be changed is the U. And this is, there's no integration here, so you just define this term as a function of n and x. And then you sum this term up and then multiply by this constant. And you should get something like this. That's initially, it's high, and it's looking like a parabolic. So high intensity in the middle, low intensity at the edge. Over time, as time increases, everything dims down to 0. So if you take the time slice, at initial time, it's a inverted parabola. And times increases, the boundary condition is met, and so the amplitude of this decreases over time. If you do a position slice, at every position, it starts up at the highest location, and it exponentially decays over time. If you do a 3D plot, it's like this. Okay, now the last section we have shown if we are given the analytic solution, now we plot the analytic solution. And in this section, we'll see how can we solve simple PDEs as an ODE using solve IVP. So consider we have a heat equation. Wait, this is the, okay, as the last problem. So we have U of t is equal to U of x. So this gives us 2 boundary conditions and 1 initial condition. And the boundary conditions are 0, and the initial condition is f of x, and f of x is an inverted parabola. We want to solve this system using solve IVP. And to do that, we want to reduce the PDE into an ODE. And to do that, we can use finite difference method. So from the definition of derivative, we have this forward difference method. And we can do the forward difference method for a second order derivative. So in this U of t is equal to uxx, we rewrite the uxx as this term using central difference of second derivative. And so we substitute this into the PDE, and now we have U of t is approximately equal to this term. So this gives us an ODE. So everything on the right we know, And on the left, we have a first derivative. On the right, we don't have a derivative. So this becomes an ODE. And to solve this problem, everything we define as the same as before, and the solve IAP makes the same. But what's needing to be defined differently is the ODE system. So let's look at how do we define the system. So instead of a lambda function, we'll define this as a full function. And again, it takes in the independent variable, in this case it's t, and the list of dependent variables. In this case, I'll say this is u. And so I'll have this u of t, initialize it as zeros like as u. This is to initialize all the values. So I'm basically initializing everything on the right as 0. And now I want to enforce the boundary conditions of u of t. So u of t, I have two boundary conditions, one on the left with index 0, and one on the right with index -1. If you read this part, if you substitute these, we found that the boundary condition on the left is 0, and on the right is also 0, which is already given. So we'll define our boundary conditions on the left as 0, and on the right also 0. And now we want to update the right part, the central difference. So what we want to do is to enforce this part. So what we have should be u of t. So u of t is equal to, at the ith location, should be equal to u of I plus 1 minus 2 times u of I plus u of I minus 1. And the whole thing divided by delta x squared. And want to do this for I in range from the beginning to the end. So this will be from 1. So initially we want to have it at 0, but 0 minus 1 will give us -1, so that will be incorrect. So we'll start at 1. So 1 minus 1 is 0, 1 and 2. So that will be correct. And then ending at, because we have, this is the x length, so we have already defined the x number of points, which is 200. That will be number of points minus 1. Because on the right, we can't have I plus 1. So we will have a -1 here. So there we're defining the right part in the interior, not boundary conditions, not at boundary. And we will return u of t. Let's give it some t and u, and it should give us a number. Too many indices. Oh, instead of a number, we should supply it with some array of numbers. Well, I should give it with the same number of x. So I'll just test this. And you can run this with the same solve IVP, defining the function, the boundary of t, and the initial condition.
Explain about how to do the division.
Yes. And so after it runs, we can run the I am sure to look at the heat map, but it's still running. So this is the result that it should give us, which is the same as the analytic equation as solution. And to read the heat map, first we orientate ourselves. What are the axes? So here on the x-axis, we have x, the position. On the y-axis, we have t. And the color represents the height, which is the u, the function u. So to read this, we can read it in two ways. We can read it in the time slice way, or we can also read it in the position slice way. When you are taking a time slice, so a horizontal slice, you're looking at some particular time, say when t is equal to 0.2, I look at this. And the function, when at the cis slice, it is a function of x. And you look at here, it's 0, and then a little bit positive, and then goes down to 0. So that looks like a parabola. But of course, we can't really read that it's a parabola. We have to verify it with this kind of time slice. But to read like a heat map, you'll hold one thing constant and look across to see the colors. And if you do a position slice, then it's with respect to time. So at initial time, it has a high value, a higher luminosity. And then when t goes on, it becomes dark, meaning that the value becomes less and less. Okay, it has been run. And this is the solution. So the hard part here is, so the solve IVP, we have already learned. The hard part is to reduce this PDE and rewrite this in terms of an ODE. And after rewriting this as an ODE, we want to write this inside the ODE system. In this ODE system, we first define the boundary conditions. On the left, we have 0. On the right, we also have 0. And then using a for loop, we update the right side with this function. So that will be u of t is equal to u of I plus 1 minus 2 times u of I plus u I minus 1 divided by dx squared. You can try this with the heat equation with another type of boundary condition. And you can verify this with the analytic solution. And here, the boundary condition is different. It's the first derivative is equal to 0. So you can't really set u of t here, the boundary condition, to 0. So instead, you want to do some derivations here. And we'll come back to this in a few moments if you guys have questions. But these are the hints.
You have the same, you have the same PDE, you have the same initial condition and boundary that you provided on the previous slide. So yeah, what's the unity with F00? Provided.
This is the tension. The last one is type one. It's the emergent functions.
So I inverted the boundary condition from UX UT equals 0 UX LT equals 0 to UT of 0T and UT of LT. I have this ugly expression and on how to proceed with it. And I don't understand, like, how do you, this is for the boundary condition for just the function, not the first derivative.
Yes.
How do I do first derivative?
Your input is you first solve this. So move this to the left, becomes 0. So this term is equal to this term. Then you substitute these in here. And you note that one end, so on the left end, you can't go back. So you don't have a x minus dx. So you will substitute x minus dx as x plus dx. So that will be 2 u of x plus dx. Minus 2.
Minus 2 U first divided.
Yeah. And then on the right boundary, you have L. So you can't go right. You can only go left. So you substitute. Yeah. And then you'll have that expression written here. Instead of 0.
So I just have to. So I just have to set this equal to 0. So I would get rid of this. I have to change this to positive 2. This would be equal to 2. Oh, positive 2.
Still need that divided by dx squared.
Oh, I still need to divide by dx squared.
And the next step is to write it in Python using the index. So in the first case, we have x plus dx and x, where x is equal to 0. So that will be index 1 minus index 0. Yeah. The first one will be index 1 minus u index 0 divided by stuff.
Oh.
And for the second line, you're on the right. So you have L and L minus dx, and L will be minus 1 because you're at the end, and L minus 1 will be minus 2. Second to the end.
That is my initial condition for UT of 0T and UT of L of T. Then how do, because this code here is for the function itself, it's not the first derivative. Then do I have to write like UT prime?
I don't think so.
Because I wouldn't have, it's not like I put the constant to this.
Mm,
I have to change this to the first derivative.
that's a good question. Write it as is for now. I'll get back to you. Yeah. Question.